All right, this is exam 4 for spring 25. I have this 2N system. I want to know where is the final position and the final magnification of the image. So first I will take it as the first lens, considering that P1 is equal to 20 centimeters. That's this distance. F1 is equal to 10 centimeters. I'm going to solve that for Q. So I have 1 over 10 equals 1 over 20 plus 1 over Q. I'm going to change that 1 over 10 to 2 over 20 minus 1 over 20 is equal to 1 over Q. So Q is equal to 20 centimeters. That means also that the magnification, I'll call it M1, is equal to negative Q1 over P1. This is Q1. Negative 20 over P1, which is also 20, so negative 1. So now if I'm drawing my image, it's going to be 20 centimeters to the right, and it has a magnification of negative 1. It's the same height as the object, but it's inverted. And this is 20 centimeters. It means that this distance is 50 minus 20, or 30 centimeters. Oops, sorry, centimeters. That means that P2 is going to be equal to 30 centimeters. F2 is equal to 15. So I have 1 over 15 equals 1 over 30 plus 1 over Q. Solve that. I'll go ahead and convert that 1 over 15 to 2 over 30 minus 1 over 30 is equal to 1 over Q. So Q is equal to 30 centimeters. That's Q2, by the way. So that's the position of the final image, is 30 centimeters to the right of the second lens. And then the total magnification of the image, well, let's get to M2. So M2 is negative Q2 over P2 is negative, what's that, 30 over 30. So it's the same. Negative 1. That means that the image is going to be 30 centimeters to the right of this lens, and it's now going to be the same size as that image, because it has a magnification of 1, and it's inverted, or it's the opposite of what it was. So that image is going to be, or the magnification then, M total is going to be equal to product of M1 and M2, or negative 1, or positive 1. So that's the right answer. Positive 1. All right. Object is 3 centimeters tall and to the left of the mirror. The image is upright and 12 centimeters tall. First, I just want to know what type of mirror is this. This is a mirror where the object is bigger than the image. Excuse me, the image is bigger than the object. So that means that it has to be a concave mirror. If you recall, that would look a situation like this, where my object is right here and my image is right there. Okay, so it's a concave mirror. That means that the focal length is going to be positive. I can go and write that down actually. The focal length is equal to the center of curvature divided by 2. That's going to be 40 divided by 2, or 20 centimeters. That's the center of curvature right there. And because it's concave, it is a positive focal length. Also, I know that the magnification is HI over HO, which is going to be HI is 12 over 3. That's a magnification of 4. And it is positive 4. We know that this image is upright. In fact, it tells us that it's upright. So it is a positive 4. Now, I want to know the image distance. And is the image to the left or right? So I know that the magnification, which is equal to 4, is equal to negative Q divided by P. I also know that 1 over the focal length, that's 1 over 20, is equal to 1 over Q plus 1 over P. So I have this system of 2 equations, and I want to solve it. I'm going to solve this one for Q. So Q is equal to negative 4P. I just multiply both sides by negative P. And now I'm going to take this negative 4P, and I'm going to put it right here. So I have 1 over 20 equals negative 1 over 4P plus 1 over P. I'm going to go ahead and find a common denominator. That's going to be 4 over 4P. So 1 over 20 is equal to 3 over 4P. That means 4P is equal to 60. I cross multiply. So P is 60 divided by 4, which is 15 centimeters. So that's my object distance. Well, I want to know my image distance actually. So I can just take that 15 centimeters and bring it back up here. So Q is equal to negative 4 times P, which is 15, are negative 60 centimeters. So that's the image distance is 60 centimeters. And is it to the left or right of the mirror? Well, it's to the right of the mirror. In fact, if I knew this, I could get that right. But it's to the right of the mirror because it's negative. For mirrors, a negative means it's to the right of the mirror. It's on the virtual side of the mirror. All right. Here I have light of wavelength of 600 nanometers. It's on a diffraction grating. Now the screen is 2 meters away. First, what is the slit spacing? Well, this describes the diffraction grating. That means that if a diffraction grating is 1 centimeter across, there are 8,000 lines. I can't draw 8,000, but you get the idea. There are 8,000 lines or slits or grooves. And I want to know what is the separation between an individual slit. To find that, I just take the inverse of that 8,000. And then that's going to be in centimeters per line, or 1 over 8,000, that's equal to 1.25 times 10 to the minus 4 centimeters, which is 1.25 times 10 to the minus 6 meters. Okay, so that's the first answer. I would take it in centimeters, but you're going to need it in meters for the next one. So if you report it in centimeters, I didn't count off, as long as you had the unit correct. Okay, and then B, what is the distance to the central maximum? Okay, so I'm going to draw it as a double slit, but it can be a, think of it as a diffraction grating. If this is our diffraction pattern, we have a central bright spot surrounded by two less bright spots, by two adjacent bright spots. I want to know the second bright spot. I want to know the distance from here up to here. I'm going to call that Y. Now, I know that the angle from here to here, that this is the angle theta. And I know the relationship between that angle, which is the path length difference, d sine theta. That is our path length difference. That is, if I have a light ray traveling that distance and that distance, the one on the bottom travels a greater distance by this amount. That path length difference is equal to m times lambda. I have 0 path length difference here, 1 wavelength here, and I have 2 wavelengths here. 2 wavelengths path length difference because m is equal to 2. And I want to solve for theta. So I say that theta is the inverse sine of m lambda over d. That's 2. Lambda is 600 times 10 to the minus 9 meters, divided by d, which is 1.25 times 10 to the minus 6, has to be in SI units. That's in meters. So you use all your proper order of operations. And when I find that angle, I find that it's equal to 74 degrees. All right, so this diffraction pattern has an angle to the second order maximum at 74 degrees. And then I want to know that distance. Well, if I draw this triangle, this is y, this is L, this is theta, then I know that y is equal to L tan theta. That is y, the screen is 2 meters away, tan of 74 degrees. That's equal to that 2 tan of 74 is equal to 7 meters. I didn't draw it very well because I drew it as an acute angle, but really it's a bigger angle, so it's really sort of like this. It's a pretty big angle. This angle, and then this is the 7 meters, and this is the 2 meters. Okay. Consider this mirror. I want you to draw 2 rays and then describe the image. You already probably know what the image is. It's a virtual upright smaller image. I can draw 2 rays. I can draw one ray that is parallel to the axis, and then it's going to go away from, it's going to diverge, but it's going to diverge in such a way such that if I traced it back, it would go through the focal point. All right, so that's one of my first rays, this ray that goes back through the focal point. We call that a virtual ray. Then I can draw another ray that is through the focal point. Watch how I draw this. I draw it forward such that if I were to trace it forward, it would go through the focal point, and then it goes back parallel to the axis. And then I can trace this ray back. That's my virtual ray. I can draw a third ray if I like. The only required 2 rays here. I can draw a ray that goes to the center of the mirror, and then it reflects back, following the law of reflection. I can trace this ray back. Notice my rays are all crossing at that point. I can do a fourth ray if you really like that center of curvature ray. I'll do it in orange. Let's see, this is a little trickier. I have to make sure my straight edge works, right? So I draw it such that if I were to trace it forward, it would go through the center of curvature. That's not a very good color. Let's do a different color. Draw it such that if it were to go through straight, it would go through the center of curvature, and then it reflects back on itself. So if I trace that back, it goes through there. So my image is right there. And that image is upright, virtual, and smaller than the object. Virtual, upright, and smaller. This is a convex mirror, so it produces that kind of image always. All right, let's look at the multiple choice. So here, where's the final image? This is a lot like the free response of a 2-lens system, except I just want to know what is Q2. So P1 is equal to 60, F1 is equal to 20. So I say 1 over 20 equals 1 over 60 plus 1 over Q1. I'll go ahead and convert that to common denominator. And so Q1 is equal to, what's that, 3 over 6, 2 over 6. Q1 is equal to 30 centimeters. Okay, so 30 centimeters is, by the way, I can go and calculate, let's just go and calculate the magnification. Q1 over P, that's 30 over 60, negative 30 over 60, or negative 1/2. All right, so my image is going to be 30 centimeters, and it's 1/2 the size of the object, and it's inverted. So that's 30 centimeters. This then, 60 centimeters. So that's P2 is equal to 60 centimeters. F2 is equal to 30. 1 over 30 equals 1 over 60 plus 1 over Q2. That's 2 over 60. So Q2 is equal to 60 centimeters. So my image is going to be 60 centimeters in this direction, centimeters, 60 centimeters to the right of lens 2. By the way, the magnification M2 is negative 60 over 60, or negative 1. So the total magnification is M1, M2, which is equal to positive 1/2. So notice I drew this the same size as this object, or I tried to anyway, but now it's inverted, so it's an upright image. Or it's inverted from the inverted first image, so now the final image is upright. All right, so that's A. Excuse me, D. Spherical aberration is caused by what? Let's see. Lights from different parts of the lens or mirror focusing at different focal points. These lenses make an image that is upright and smaller than the object. Okay, so let's think about what type of lens this is. Lenses can only make 2 types of upright images or virtual images. The convex lens, if I have the object in front of the focal point, it creates an image that is upright and virtual. The concave lens, if I have my object, it produces an image that is upright and smaller, a virtual image. So those are the only 2 virtual images. Notice, by the way, that those virtual images are on the same side as the object, on the left side of the lens, because that is the virtual side of the lens. This is the real side, and the virtual side is on the same side as the object. But anyway, all that to say is that this situation, making an image that is smaller than an object, is the concave lens. And concave lenses have a negative focal length. So the center of curvature of this is 60, So the focal length is negative 60 over 2, or negative 30 centimeters. It's negative because it's a concave lens. Uh, the object is 30 centimeters, and so I want to know what is the magnification of the image. Well, I already know that the image is smaller and that it is upright. So if you're really savvy about this, you could say that the answer has to be D. Okay, and hopefully you're able to see that none of the options are possible except for D. However, let's just go through the calculation. Say 1 over negative 30 equals 1 over 30 plus 1 over Q. That's negative 1 over 30 minus 1 over 30 equals 1 over Q. So Q is equal to negative 2 over 30, negative 30, negative 15 centimeters. So that's Q. And the magnification is negative Q over P is negative 15 over 30, or positive 1/2. Let me show you what you would have gotten if you had gotten the focal length wrong. That is, if you thought that it was a convex lens instead of a concave lens, you would have said that the focal length would have been positive, in which case it would have been 1 over positive 30 equals 1 over 30 plus 1 over Q, in which case you would have found that Q was equal to infinity, and you would have said that E is the right answer. But it's not, right? That would be incorrect because that would be saying that my focal length is positive when really my focal length is negative. All right, concave lens has a focal length of 30 centimeters. Okay, so F is equal to negative 30. Concave lens has a negative focal length. The object is 30 centimeters, and I just want to know what is the image distance. Um, isn't this the same problem that we just did? It is. So I'm just going to go ahead and write A is negative 15 centimeters, right? 1 over negative 30 equals 1 over 30 plus 1 over Q. You have a convex lens with a focal length of 20 centimeters. So that focal length is positive 20 centimeters. Convex lens, positive focal length. So a lens like that. I hold an object at a distance of 10 centimeters from the lens, centimeters. Okay, so I can I can get rid of several options here because I know if my object is in front of the focal point like that, that's my object, that my image is bigger, upright, and virtual. So I can get rid of that one and that one. So it's either A, D, or E. Now, I need to go through the rest of it. 1 over 20 equals 1 over 10 plus 1 over Q. That's 1 over 20 minus 2 over 20. I just changed that 1 over 10 to 2 over 20 equals 1 over Q. So Q is equal to negative 20. And then M is negative Q over P. Negative 20 over P, which is 10. So it's positive 2. A is the right answer for 5. You stand 100 centimeters in front of a mirror and find that your image is twice your actual size. Okay, what kind of mirror is that? That has to be a, um, a mirror that is a concave mirror. Okay, so notice here a couple things. Uh, it's concave mirror because that's, if this is the object, this is the image, that's what kind it produces. And then also notice that I'm 100 centimeters in front of the mirror and I want to know the focal length, but I have to be at a distance closer than the focal point. Oh, so none of those fit that, right? Some of them are negative, but I know it has a positive focal length, and some of them are less than 100. But I know that my focal length, because this distance I'm telling you is 100, my focal length has to be something bigger than that. Okay, so you wouldn't really have to do this, but let's go ahead and work through it. P is equal to 100. Magnification I know is positive 2 because of the type of mirror that it is. It doesn't tell me that right away, but I know that the only mirror that produces an image that is twice as big is one that's has a concave mirror, and it has a positive focal, has a positive magnification. And I want to know the focal length of the mirror. Well, I know that M is equal to positive 2. That's also equal to negative Q divided by P, or negative Q over 100. So Q is equal to negative 200. Now that I know P and I know Q, I can find f. 1 over 100 plus 1 over negative 200. I'm going to make this 2 over 200. And I find then that f is equal to positive 200. All right, you look in a mirror and you see an image of that's smaller than you really are. Which of these options gives the type of mirror? Well, if I'm looking in a mirror, that means that I'm smaller. That means I'm looking at a convex mirror. So it's not that. It also means that I'm looking at a virtual image. Virtual images are always upright, and it's an upright image. So C is the right answer for 7. Mirror is an upright image that is 1/2 the size of the object. All right, so again, that's a convex mirror. Um, the object is 6 meters away. The magnification I know is positive 1/2. By the way, I also know that the focal length of this mirror is negative, so I can get rid of B and D because it's a convex mirror. Convex mirrors have a negative focal length. Um, this is equal to negative Q over P. So that's 1/2 equals negative Q over 6. So that's negative 2Q equals 6. So Q is equal to negative 3. And now I know P and I know Q, I can find F. 1 over F equals 1 over Q, 1 over P plus 1 over Q. That's negative 1 over 3. I'm going to go ahead and make this a common denominator of not 1 over 3, but 2 over 6. So 1 over F is equal to negative 1 over 6, or F is equal to negative 6. So A is the right answer for 8. All right. What type of mirror will form this image as shown? All right, we've seen this already. This is a, excuse me, not a convex mirror. I did that wrong. A concave mirror. When you're inside the focal point of a concave mirror, it produces an image that is upright, bigger, and virtual. What are the correct rules for drawing rays to a spherical mirror? Ray goes parallel to the axis and reflects to the focal point. Correct. Ray goes through the center of curvature and reflects back on itself. Yes. Goes to the center line of the mirror and follows the law of reflection. As we said, the rays always follow the law of reflection, but that one's just easy to draw. A ray goes through the focal point and reflects back parallel to the axis. That's correct too. In fact, we drew all those rays on the Fourier response, or I did. So E is the right answer. What's that? Number 10. Consider the lens with 3 rays. The focal point and center of curvature are labeled. Which ray is correctly drawn? So let's look at these. Ray A goes parallel to the axis. It should go through the focal point. Oh, but it doesn't. So A is not right. B goes through the center of the lens. Okay, so B is okay. It goes through the center of the lens unrefracted. And then C goes through the focal point and then parallel to the axis. So B and C. In fact, once I knew that B was the right answer, I knew it had to be B and C. All right. What kind of lens would you use to create a magnified image? That would always be a convex lens. Diffraction grating has a slit spacing of 1 times 10 to the minus 6 meters. The first order is at 14 degrees. And I want to know the wavelength. I just say d sine theta equals m times lambda. So that's d 1 times 10 to the minus 6 sine of 14 divided by m is equal to lambda. And if I do that, I get 242 times 10 to the minus 9. Diffraction gradient has 2,000 lines per millimeter. What is slit separation? 1 over 2,000 is 5 times 10 to the minus 4 meters. That's not an option, but I'm in millimeters. I can just change that. 1 meter is 1,000. Hold on. I see. So let me fix this right quick. I wrote the units wrong here. So it's 5 times 10 to the minus 4 millimeters. and then 1 meter is 1,000 millimeters. So it gives me 5 times 10 to the minus 7. I do that. All right, number 15. What happens to the diffraction grating if you use a diffraction grating with a smaller slit separation? Or what happens to the pattern if you use a smaller slit separation? Look at this, d sine theta equals m times lambda. If this goes down, that's what I'm doing, then this quantity has to go up. So theta gets bigger, which means that my pattern, which may have looked like this, right? Remember the angle is the angle from here to here, that if my angle gets bigger, then my pattern gets elongated. I'm exaggerating here. It gets spread apart. So I might have bright spots here, here, and here, but then I'd have bright spots here, here, and here. So as D goes down, theta goes up, and the bright spots move apart. So double slit diffraction pattern, what's the path length difference? Well, this is 0 wavelengths. This is a half a wavelength. This is 1 wavelength, and this is 2 wavelengths. By the way, this is 1.5 wavelengths, 2.5, and on and on. So it's 2 wavelengths, D. Light of 500 nanometers, center double slit, was the highest order present. Whenever you see this highest order, you think, well, what is the order when theta equals 90 degrees? Because if I think about my double slit or my diffraction pattern, the angle right here, theta, when it exceeds 90 degrees, that would be this angle, then the light is no longer incident on the screen. So, and you're not going to get any patterns. So I just say d sine theta, d sine of 90 equals m lambda. And I want to know what m is. So m is equal to d divided by lambda, which is 500 over 1,000, or excuse me, 1,000 divided by 500. That's equal to 2. If it came out to be some number that was not an integer, say if I got 1.7, then the answer would be 1, because you can't have 7/10 of a bright spot. Just like you can't have 1.5 kids, you can only have 1 kid or 2 kids, so you round down, not up. Two waves are initially in phase and have a wavelength of 4 meters. One wave travel is 1 meter and the other wave travels 3 meters. So my path length difference is 3 minus 1 or 2 meters. Notice that this path length difference is equivalent to 1/2 of a wavelength. So I'm going to see a dark spot at that point. Consider these superposition of these two waves. All right, so when these two parts of the wave add up, they get nothing. So that would be here, 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 and here. That doesn't help us. Those are all okay. When these two parts of the wave add up, you get something that looks like that. So not that one, but these two are okay. And here I get 3 parts. So this adds up a trough with a peak, so I get nothing. A peak with a peak, so I get a big increase, and then a peak with a trough, so I get nothing. And that's going to look like this. So A is the right answer. And then who is my favorite student? And these are some great students that I've had in the past, but you're my favorite student. I'm really grateful for this year. I hope you'll have a wonderful summer. Well, we'll still have the final, but it's been a really good year to know you and to learn physics with you.